So today we start discussing group representation theory proper. We'll actually start with a brief mention of something else, but as you see, it will play a role. So in general, when you're talking of a representation of a group, it means you have an abstract group and you see somehow the elements of the group as function, as functions acting on a certain set. This is actually, as I probably mentioned already, a sort of a reverse of what happened historically, because groups were born as permutation groups, say permutation groups, for instance, of the roots of a polynomial equation, and only later become abstract. And this goes in the opposite direction then. I mean, you have an abstract group and you see it as a group of something. So the first thing we are going to mention are, well, we will call it permutation representation in the end, but say group actions. These are important for two reasons, because they will provide important, extremely important examples of linear representations. So of the representation we are interested in this course. And moreover, they have a dual definition that mirrors a dual definition of linear representations we will have later. So what's a group action? A group action can be given in two equivalent ways. I only recall this briefly because I assume you have seen it in other courses like my theory of the group or something else. If there is any need to repeat something, just let me know. So the two equivalent ways are, okay, so let's say omega is set, omega is a set, and G is a group. Okay, omega is a non-empty set. And then a map omega times G to omega, which associates to a pair of an element of omega, an element of G, and an element of omega. And as you will remember, one normally does not write this map as, say, F of alpha G, but simply as alpha to the G. But this is just a shorthand to mean the image under this map without the name of the pair alpha and G. Oh, by the way, if you have done algebra with me, I mean, I tend to use right actions. There is the G is on the right. If you've done it with Willem de Graaf, he tends to have to use left actions. So the G would be in front here. But I mean, they are, of course, absolutely equivalent. So one definition of an action is such a map which satisfies two axioms. And so the first axiom is that alpha to the one being, of course, the identity of the group, is alpha for all alpha in omega. And the second one is that if you apply G to alpha and then you apply H, then you get, this is the same as applying the product GH to alpha. Okay, so this is a composition of function. Here alpha is in omega and GH for all, of course, okay? And so this is a definition of an action, but an action can be given also as a morphism, a group homomorphism from G to S of, sorry, this is a misprint, S omega, where this is the group of permutations, bijective maps on omega. And this is important since I have right actions. You see, if I apply to alpha the product GH, you can see this is the right action because it's G that acts first and then H. okay? Whereas function composition, say in analysis, usually done the other way. So group permutations on omega with the left to right composition. This is a technicality. So meaning that as I said, when you have a product GH, the first to act is G, the leftmost one. I mean, so these two are equivalent. And we will see that when we get to group representations, we will have a linear representation. We will have two way of defining them that is similar to this one. To this one you're used to. There are two important representations. One of them is absolutely important, as you will see. So examples, the right regular representation. And this is usually written as rho, the Greek rho. The point is that rho is also the preferred symbol for a representation, R, rho for the initial R of representation. So I will write it in the notes is some Gothic R, so a R like this. So I use the second version of group actions. This goes from G to S of, what's the set? It's G itself, okay? Why is it called a representation? Because as I was saying at the beginning, such a map, for instance, G to S omega, represents an element G as a function on omega, okay? So via this map, I can see an element of G as a permutation on omega, representing an element of a group as a function. So this is in this case, a permutation on the set G. Okay, this is just the set, usually called the underlying set. So a group G is a set, then an empty set with certain operations, and this is just a set. And what does this map do? This sends an element G to the right translation by G. It means it's to the map that sends X to XG, okay? So this is usually carrying operation. I mean, the map associated to G is the map that sends an element X of G to the product XG, okay? And as we will see, this is an absolutely essential representation also in linear representation. Let me mention that there is also the left regular representation. Okay, which is some L, distorted L from G to SG, and this sends G2. And okay, the first thing I will write is not quite correct. You may think, well, of course, if the right multiplies on the right, the left multiplies on the left, but this is not a right action anymore. So I need an inverse. If you check, I mean, with an inverse, this becomes a right representation. Otherwise, it's a left representation, because if you don't have the inverse and you have a GH here, it's H that multiplies X first and then G, whereas I want the opposite. Okay, so this is all about group actions. It's important to have these two different views, and we will see the crucial role that the right regular representation will play in the following. Good. So let's go to the next page, and let's define the core argument of the course, linear representation. And so the idea is the following. G will be a finite group. I will mention another kind of group, compact groups. I mean, you can basically do the same theory I'm doing, well, part of the theory that I'm doing here, also in other contexts. For instance, the context of compact groups. And compact groups are the subject of one of the seminars. I mean, you can check the list of seminars posted on the site. So G, a finite group, V, a finite dimensional vector space on the complex numbers. Let's say if we, okay, let's say of dimension n. Okay, note that we will see quite quickly that C is absolutely essential here. If you change the field, you get a different behavior and not as nice as we get here. So a linear representation of G, let's say of degree n of G. So that's the term, the critical term we are going to define. It simply is a group morphism rho from G to GLV. Now, abstractly, this is the group of invertible linear maps on V. What we will very often do, we will choose a basis of V. This is a finite dimensional vector space, so a base with n elements, because n is the lattice we are reserved for the dimension. And then in practice, we will have G, Ln, C. So this is the group of n by n invertible matrices with the determinant different from 1, with coefficients in G. And C. Okay. Well, of course, this equal it has to be taken with caution, because you can this abstract, and then to go from this to this, you have to choose a basis, and then you can get different things. Okay. In the rest of the course, I will simply speak of a representation, because I mean, we will only be dealing with linear representations. I will be talking soon of permutation representations, but this will be particular linear representation. So when I say representation, I mean something like that. Okay. And okay, fine. Let's note a few immediate consequences. As usual, since rho is a morphism, so a group morphism, we will have rho of, if rho is a representation, rho of the inverse is the inverse of the image, okay, for G in G. But there is another important thing, that if I let the order, well, in the notes, the order of G is n, which is a mistake. I will try and correct it. Let it be k, okay? Because I mean, I cannot use n, of course, for two different things. Then you remember that we'll have G to the k, G to the power, k's power to be 1 for all G in G. And so we will have, since this is a morphism, we will have that 1 equals rho 1 equals rho of G to the k, but this is a morphism, so rho of G, sorry, too much, to the k. I mean, this is after all a product, okay? So what we are seeing here, I'll now mention some linear algebra. If you have any problem with anything of linear algebra dimension, please let me know. What we find here, we find that rho of G is a root of the polynomial x to the k minus 1, which is a polynomial, well, coefficients 1 or minus 1, but of course a polynomial coefficient in C. Okay, because exactly what I've written here, rho to the G, rho of G to the K minus 1 is 0. So it's a root of this polynomial. So in particular, it's the minimal polynomial of rho of G. I'm assuming that I'm here in matrices. Oh, well, of course, it would be the same here. So since rho of G is a root of this, then this implies that the minimal polynomial of rho of G divides x to the k minus 1. Okay, let me, I'll be back to this page, of course, because the idea of the minimal polynomial associated to each matrix or to each linear operator, the linear map, there is a polynomial which is the small, say it's polynomial, monic polynomial of smallest degree, which has the matrix or the linear map as a root. Since rho of G is, and this minimal polynomial, exactly as in the case of algebraic extension, divides all polynomials that have rho G as a root. So since rho G is a root of xk minus 1, this means that the minimal polynomial of rho of G over C divides sk minus 1. But this polynomial has distinct roots, okay? Because these are the case roots of unity in C. And you see why C is important here, because if I were doing the same over R, for instance, I wouldn't, well, okay, it's still true, but I mean, I wouldn't have the roots in C. Okay, we'll see in a second. So it has distinct roots. The minimal polynomial divides this, so the minimal polynomial of rho G has distinct roots. And this implies that rho of G can be diagonalized. There is a root, there is a basis, or base or basis of the vector space. There is a vector space hanging around with respect to which rho of G is diagonal. Okay, so I choose a basis, I get different matrix representations. Okay, and this is an important thing, and we will see something happening in a second. But before we continue, we have to introduce, or actually the next thing is introducing an extremely important tool. And what's this? I mean, I'm going to use inner products and unitary operators and the like. I have written in the preliminaries something about this to remind you. If you need anything about any more details, just let me know. So the point is, this is a relatively simple but important theorem. We are assuming that we have a representation and so on. There is an inner product on V. I assume you recall what an inner product is. If I mean, if in case, just ask me. Such that the rho G, all the rho G, are unitary matrices. So I had started by, I'll be back in a second. Representation is a map from, is a morphing from rho from G to the group of linear maps. But by choosing a suitable basis, you may assume that you are going into the unitary group, the group of unitary matrices. And this is an important restriction. Why is this important? Because we will see that this allows us to give proofs, easy proofs of facts by using geometry, by using the inner product, okay? And so let's see this proof. And the proof is very important because although it's not difficult, it introduces a tool that is extremely important. An averaging trick, actually, that is extremely important. So we start, let us fix a basis. I write base or basis, depending on the mood of the moment. A basis of V, and consider the standard inner product with respect to this basis. Okay. Which means that if we write vectors in V in coordinates with respect to this basis, okay? So I write the vectors. My vectors are line vectors, and most of the time I use brackets, square brackets for these vectors. So x1, xn is one vector, and y, it will be y1, yn, okay? So I have fixed the basis, and these are the coordinates of two vectors with respect to the basis, and then yes, well, okay, and then the standard inner product will be So these are row vectors. So it will be the conjugate of x times y transpose, okay? So what does it mean? So that we review this. So a conjugate of the vector means conjugating every element, and then I transpose y. And this will, of course, will be the sum of xi conjugate times yi, okay? So that's the standard product. So you see, for me, an inner product is linear in the second component, and what is called the sesquilinear with respect to the first. There is you don't get you get a conjugate, okay? The elements are conjugate. Okay, so I fixed any basis that I fancy, and I've taken the standard inner product. There is no chance that my matrices will be unitary with respect to this scalar product, the inner product. But then I define another inner product well, I will leave to you to check that this is actually an inner product. I will write it as double angular brackets. Well, I could make an average. Later I will take an average, but here you don't need to take averages. This is the sum for over G in G of the following: X rho G, Y rho G. Okay. I could average, but it must mean later it's really important to put an average. There is to divide by the order of G, but here is not important. I mean, please check that this is another inner product. And this is now a very important property. Why? What is this property? Well, to show that the row G are unitary with respect to this new inner product, I have to take an H in G and show, and here there's a question mark, that this equals the scalar product, the inner product of X and Y. This for XY in V and for H in G. This means that the row H are unitary. So this has to be proved. Let's see how it works, but it's a trick that you that you should know. So what's this product? I take this definition, is the sum over G in G over what? Well, this time instead of X and Y, I have X rho H and X rho G. Let's go, sorry, and Y rho H. And now, well, I could have taken more space. Well, okay. Now I know that, of course, rho, remember, rho is a morphism, okay? So rho H rho G is nothing else but and then I do a change of variable, because you see, I'm summing over G in G, but essentially what I have here is the image of G under the, well, not quite, the left regular representations. I mean, it's quite clear that I can change a variable, because as G, once H is fixed, okay, as G ranges over G, these elements range over G, okay? The reason is being that, of course, that this map is a bijection, okay? For given H and H, this is a bijection. And so all the elements of G are this form. It's the thing we use, for instance, to show that all cosets have the same cardinality. So if I change variable, I will do it here. I can say, let's call this variable X. This is the sum for X in G. No, not X, that is very bad. K, X rho K, Y rho K, okay? And of course, this a dummy variable, variabile muta in Italian. I mean, I'm simply summing here overall elements of G. Whether I call an element of G little g or little k is absolutely the same. So what's this? This is nothing else the thing I had at the beginning. I mean, not at the beginning, but this product. And so I approved, in fact, that this equals this, okay? So this means that rho H is unitary with respect to this. This is a very simple argument, this averaging argument, but we'll see that it's quite powerful, and that we'll be using it for several things, okay? So perhaps I should note something else let's see. Well, okay, I'll talk of this from. I'll discuss this later. There's no reason to discuss it here. Okay, so we will be using this fact in an essential manner tomorrow. So if I wish, I can consider the images of a representation as unitary matrices, as members, as elements of the unitary group. Okay. Now, we will discuss in examples, okay? Very simple examples at the beginning. And the idea is to show how you go from actions, say, to linear representations. And for simplicity, take omega to be the set 1 to n, okay? Let V be a space, a C vector space. All vector spaces will be over C under, unless I say otherwise, of dimension n, and basis, let's say V1, Vn, okay? Now, suppose G acts on omega, okay? Actually, yes, okay, fine. It's not important. G acts on omega. Then I can define a linear representation rho from G to GLV. Okay, so that's a linear representation. And no, okay, what's this linear representation? We know that to give a linear map, because I mean elements of GLV are linear map, I have just to declare it on a basis. And such a linear map will be invertible if and only if the image of a basis is a basis itself. So what I do, I take a permutation of the basis elements. I send VI to VI, oops, I have to fix the notes because I G minus 1. Perhaps you've seen this already. I have the I don't remember whether I told you in the previous lectures, but for some reason you need an inverse here, so that this is a right representation, say. Okay. Well, I'll discuss it when it matters. So what I do is I take the elements of a basis and I permute them according to the action I have on G on omega. Okay. And actually, I can do this for every set. I can do it for any omega. I started with omega being 1n for simplicity, but I can do it. I can do the same for any set of size n. Okay, if I label for any set omega of size n, if I label the elements of the elements of a basis of n of v by the elements of omega. Well, let's start with an example. Okay, it's a very simple example, but so consider the group G to be the cyclic group of order 2. Okay, and so G will be generated by an element G, which is order 2. So G has exactly 2 elements, 1 and G. So consider a vector space V of dimension 2 with bases. Well, V1 and Vg. So the basis is not indexed by the first natural numbers, the positive natural numbers, but the element, by the element of the group G. And then consider the linear representation rho from G to GLV. We send G, as I said, to the maps that send VI to the G inverse. Okay. Okay. So, well, that sense, sorry, not G, because G is a specific element. So let's say X. Okay. Of course, since this is a morphism, rho of 1 will be the identity, okay? So it will be the identity matrix. No need to discuss anything here. So what only matters here is what's the image of G. And what is the matrix of rho of G in terms of the basis. So what is the matrix of rho of G with respect to the basis? V1, Vg, okay? So the idea, of course, is simple because I take rho G and I check where it sends V1 and where it sends Vg. So it's written here, V1 goes in V1G inverse, okay? Oh, yes, but I forgot to mention something. Okay, sorry, I forgot to mention something. Because I have this cyclic group of order G, and this is important, okay? So the group G acts on the set G, but via the right regular representation. What I'm writing next is sometimes a source of confusion. When I have I mean, alpha to the G is a generic symbol for an action, okay? In this particular case, when omega is G itself, no, I cannot write it there because I need space for something else. This is just the product, okay, inside G, okay? So, was this 1 times G inverse? Well, G has order 2, so this is just Vg, okay? So the idea is, let's check with this G inverse, okay? This is a generic symbol for an action, but in this case, G acts on itself via the right regular representation. There is G is sent to the map, which sends X to Xg, okay? So what does G inverse to G do to G? It multiplies on the right by G inverse. So this is V1, okay? So what's the matrix, the corresponding matrix? Well, remember that I use row vectors. So to build the matrix, it will be a 2 by 2 matrix because I have a vector space of dimension 2. To build a matrix of this linear map, I label the rows by the elements of the basis, and I label also or say, okay, V1, Vg, V1, Vg. So these are the labels of the row and columns. On the first row, I will write the coefficients of the image under rho G of V1. Now, the image under rho G of V1 is just Vg. So the coefficients are 0, 1, because rho of G sends V1, okay, to Vg, which is 0 times V1 plus 1 Vg, okay? And similarly, rho G sends Vg to V1. So Vg is sent to V1, which is 1 times V1 plus 0 times Vg, okay? And so we see that we have found our first representation, which is simply the representation sends 1 to the identity matrix. This is always the case because it's a morphism. And the rho of G was an element of order 2 to this matrix. Of course, this matrix has order 2 because, as you see, it just exchanges the two basis elements. So if you do it again, you will get 1, okay? And let's mention immediately an important, I'll probably have time to see this. What we'll try to do is something similar to what we have done with composition series and principal series. There is decompose, in some sense, a representation in simpler representations, okay? So suppose, let's say, sub-representations. This will become clear in the next few lectures when we give an equivalent definition of linear representations. So suppose we have a representation is a representation, okay? When I say representation, I mean linear representation, and let W be a subspace of V, okay? Now, of course, we have rho G, which is a subgroup of GLV, okay, because this is a morphism. And so the rho G is a set of maps on V, and of course we could do the usual thing, restrict rho G to W. But as usual, when you restrict a map, you can restrict the domain, but not the codomain, okay? So for instance, just to come to our previous example, if I restrict this map to the subspace generated by V1, okay, if I restrict rho G, this will map the subspace generated by V1 onto the subspace generated by Vg. That is, will go outside the subspace generated by V1, okay? And similarly, if I restrict rho G to the subspace generated by Vg, this will go outside because it will map it on the subspace generated by V1, okay? So suppose that for all W in W and for all G in G, you have W rho of G in W. So what I've written here is something I mentioned previously, but let's make it clear here. To me, vectors are row vectors, okay? So what this means, this is a 1 times n vector, okay? N, as usual, will be assumed to be the dimension of underlying space, unless I say otherwise. So these are row vectors, 1 times n matrix, and this is an n times n matrix, okay? And so, of course, you multiply the row vector first by the matrix, okay? I'm afraid you usually have column vectors, and so you multiply them on the right, but sorry, I do like this. So suppose that for all W in W and for all G in G, you have that the image of an element of W under rho G is still in W. What this means that rho G restricted to W is a map from W to W, and of course a linear map, okay? As I said, I mean, unless you have this, you cannot control what happens when you apply rho of G to an element on W. Then you say, then we say two things. We will repeat this tomorrow. Then we say that W is invariant under rho G. Okay. And this is clear what is meant here. It means exactly that that if I start with an element on W and apply an element on rho G, I still land in W. And then in this situation, I get what I call a sub-representation rho W from G to GLW. Okay, so I get a representation with values not in GLV anymore, but in GLW for W subspace, which could be smaller. And this is exactly the representation that takes G to rho of G, which is, of course, so far an element of GLV, restricted to W, okay? Or for, but perhaps I can never remember, I think it's here. There. So this is the restriction, okay? Rho G restricted to W. And when you restrict it to W, you get a map from W to W, and because the determinants multiply correctly, this will be then an element of GLW. And what I plan to do first thing tomorrow is to show that that in this situation, although I don't have invariant subspaces. I mean, V1 is not an invariant subspace. The subspace generated by V1 is not an invariant subspace, and neither is the subspace generated by VG. But I will find two complementary subspaces that are rho G invariant. Okay, and this has to do with the eigenvector decomposition of this matrix. But this will be the subject of tomorrow's lecture. That's all for today. Thanks for the attention, and see you tomorrow.